Thanks, Kevin, and thanks, Boumediene, for the invitation, both to the workshop and then also to fill in for our friend who's not feeling well today. So I don't know if I can live up to all the other talks, so I thought I would at least try to compete in the humor department and mirror Giannis's title, which I found wonderful. But yeah, I'm gonna tell you about sort of some of my PhD work on learning dynamical systems. Okay, this is me preaching to the choir, so I'll do it so fast. Machine learning is awesome if you have enough data. Physics is also awesome if you know how things work, so you can use that instead. Right now, at this point, I think most of the open prediction problems, we only have some data and we have some knowledge, and that's basically the problem. So we don't have enough to just do one or just do the other, so we gotta combine them. Okay, so that's kind of what I pitched for my PhD is, okay, how do I do something along these lines of moving us forwards in this direction? Okay, so the type of problem that I'm going to be interested in today is very simple. Let's just say that there's an ODE that I'm interested in nature or somewhere, whether it's in climate or physiology or celestial mechanics. This is super ubiquitous. So I'm interested in ODEs, and what do I want to be able to do? If you give me noisy observations of part of this ODE, doesn't necessarily have to be a multi-scale. Think of epsilon as 1, doesn't matter. If you give me noisy observations of part of it, I want to learn a model of some kind that is predictive for the future dynamics of that observable. So pretty general goal. This is something that people have been talking a lot about throughout the week. What are some of the constraints of this challenge? Again, you're going to give me only partial and noisy observations, so I don't see the whole thing. That's could be complicated. And I don't know anything about this unobserved states. I don't know why. I don't know the rules that govern it, G. I don't even know its dimension, right? I just know that maybe there's something that is causing the variables I do observe. Okay, and furthermore, maybe my observations are irregularly spaced and noisy. So I want to be able to cope with that. And I also want to say, well, what if I know something about FDAG? I don't know everything, but I know something. So how do I leverage whatever knowledge I do have? Okay. Okay, so this is my high level. I made this slide last night based on, throughout the week, I've been thinking about what are the core methods here. And so how do people, I broke it into 2 axes. So what do people do? I think one thing that people do, think back to Tokens, is you introduce delays, right? So if you give me partial observations xk, I can line them up, and then I can propagate dynamics 1 step forwards using some map. And we can try to learn that map in all kinds of crazy ways. You can use neural nets, GPs, polynomials, random features. A function approximator is going to find it, or can, right? So this is a way to do it, right? What else can you do? A different spirit. You know that there's missing variables, so you can augment the state space, right? And so now I'm creating this hidden variable R. I'm not promising you that it's Y, but it tries to capture what Y is doing. And so what kinds of methods do this sort of jazz? Well, you've got recurrent neural nets and reservoir computers and things like this, right? They augment the state space, couple it back to the dynamics. But and the particulars are really in how you choose these functions, like psi1 and psi2. Right, so for reservoirs, we saw a specific structure for psi2 and then a linear structure in psi1. LSTMs have a different structure for psi2 and so on. But you could also just imagine psi1 as a neural net, psi2 as a neural net, or both of them as GPs or random features, right? As long as I pick a big enough hidden state, I should be able to do okay if that's where the system came from. Okay, so that's the discrete time perspective. And then all of this can just be lifted also to continuous time. Maybe like methods that are defined in continuous time. Good. So in that case, what is the delay perspective? Still Tokens, or you might call it Mori-Swansig in this setting. So I just have an ODE now, x dot, but now it's a function of the path history, right? And it's a continuous, in general, some people call it distributed delay. So it's a history of the whole path. And again here, let me go back. So here f now is actually a functional, right? It takes in a whole function, which is like a path history, and outputs a number or a vector field. And again, you can do that with, so now this is an operator or whatever, but you can do it with neural nets or, Again, you can have functionals that are neural nets or functionals that are GPs or functionals that are random features and so on. So you can use different models there too. All right, and then the final kind of spot here is, well, you can also take the augmented state thing and then switch it to continuous time, and lots of people have shown this as well. People might call this a continuous time RNN or a continuous time reservoir if I choose F1 and F2 in special ways. But again, the same thing that I mentioned before. F1 and F2, as long as they're function approximators, I'm going to get back some ODE. and maybe it's actually close to the one that I initially was searching for. So I think there's a lot of work that focuses on each of these. For me, I really tried to focus on this one because I think there's less done here so far. And this kind of connects to recent work on like neural ODEs and stuff like that. And so I was just trying to ask the question is, if you gave me this data, XK, partial observations, how do I go and learn you an ODE, right? And it turned out it was a little harder than I thought. So one other thing is I told you I wanted to be able to leverage partial knowledge of dynamics. Well, what does that mean to me? To me, that means that I started with that F dagger of X and Y. What if I have some kind of nominal model F0 that you hand me? Maybe this is your reduced order model, or you have some intuition about the mechanisms of how this X system works. So you hand me a model F0, I can go and try and learn corrections to it, right? And I didn't lose any generality. I just rewrote equation 1, which was this X and Y coupled system with an F0. If you picture F0 as 0, then I've done nothing. If you give me an F0 that kind of shortcuts me to some of the right answers, now maybe I'm doing better. And I really loved Charles Lee's. He set up a nice sort of perspective here, which is about learning theory, right? When is it easier to learn stuff? Well, when the complexity of a function within your function class is smaller, right? So if perchance I pick an F0 that reduces the complexity of the right-hand side, in other words, like the residuals might be simpler than learning the whole thing from scratch, then the learning problem gets simpler. And so to me, this is the answer to, somebody asked a great question to Edot in the first talk of the first day, which was, how did you take a bad physical model that looked like crap, and how did you take a bad echo state network that looked like crap, and then you mix them together and suddenly it looks awesome? Like, this is the answer, is that they were complementary in exactly this sense. They have a correction. And so there's much less, oops, I'm like flying through. So they started with an F0 who in a chaotic setting actually diverges from a trajectory super fast, but it's only missing a simple term that needs to be learned. And that thing is easy to learn. Okay, so this is kind of the perspective on, this is also what Janis calls gray box modeling, right? So we have a paper on this and he's our first citation, right? People have been doing this since the early 90s, and that's good news to us. That means that we're doing the right thing, right? So, okay. Now I'll kind of simplify this a little bit and tell you like how I'm gonna just estimate an ODE, okay? Or learn an ODE from data. So I'm gonna rewrite this equation on the left as I'm just gonna concatenate the top and the bottom and have a new variable u. So x and r together are now just a state variable u, and I observe only some components, or I take some projection, and so that's h, right? So now I have a really simple problem. I have u dot equals f of u with some parameters theta. Maybe that's a neural net's parameters, maybe it's random features, polynomial coefficients, etc. Okay, now let's say I have noisy observations z, right? So not only am I looking at partial observations, but it's also noisy. Okay, well, let's just quickly define some notation here. I have a solution to my ODE u dot, right? So this is it. So u of t, given some initial condition v and some theta, solves this system. Cool. Okay, so what's like the simplest thing you might try to do? If I gave you data, z of t, which is noisy partial time series, I'm gonna say, okay, well, I need to find a theta that when solved through here and then projected with my h matches the observations. This makes sense. There's one little problem, which is I didn't tell you where to initialize this ODE, right? And if you fully observe the system, then yeah, you probably know where it starts, more or less, especially if it's not noisy. But I didn't observe these missing components are. So one simple thing that you can do, and this is how the original kind of neural ODE paper framed it in the, what is it, NeurIPS, would say, oh, well, you just need to learn the initial condition too. That's a parameter. So they throw it into Atom, and they say, okay, I'm going to minimize over all the parameters and the initial conditions. This is a little rough to do. Imagine you've got a chaotic system. You just try and fit a trajectory, and you're going to optimize over initial conditions. This is a super sensitive thing, right? And you're going to fly off the trajectory, and then you can't see any errors after that anyway. So they said, okay, well, maybe we should chunk it. So because of chaos, I'm worried about like long-term predictions, but I can still deal with small windows. So that's all this K is. So now I'm just going to look at little chunks, just kind of small windows of a long time series. And so you can still do the same thing. And then you just try and estimate initial condition at each chunk. And if you get the right one, and then you'll find a good solution, right? If I have enough dimensionality in my hidden state and enough expressivity, then of course the ODE is there, right? I'm dense in the original space. But it turns out that this inference also doesn't work so well if you just throw it into Atom. And so I tried to ask the question, like, what is good at estimating initial conditions? Well, that's the problem of data assimilation, right? I know that all the neural network people tell me that I got to use SGD. That's how you estimate, parameters of a neural net. So I'm going to believe in that. But I also know from personal experience that I can estimate initial conditions really well with a variety of data assimilation algorithms. And so I tested, I compared it to SGD, where I used the real equations and just said, okay, using real equations, how good is like SGD as a data assimilator? It's brutally bad, knowing all the rules of the system, right? These sequential state estimation schemes are designed to be efficient and good at doing that, okay? So here was the basic idea, is say, okay, well, what if instead we train this whole guy, but we use initial conditions that come from a data assimilator, okay? And so let me just make that concrete. So I'm going to have an initial condition m hat, which is just an estimate of the state u, given a history of partial and noisy observations, and given a current belief about the dynamics and some boring assumption on the initial condition, right? And so what that means is that my initial condition is a function of the dynamics, and it's a function of my data assimilator, okay? So that's fine. So I can just plug it in. All I did, this looks worse, but all I did was I plugged in that function for my initial condition, and now I say, okay, I still want to match the dynamics. Okay, well here's sort of, so here's kind of the trick, is that this m function, which applies data assimilation to data using my nominal model, can be written in an auto-differentiable way. And what's great about that is that now when I compute this loss, when I compute this loss, I can actually do backpropagation through the data assimilator and account for the errors in my initial state estimate. And if you guys are familiar with this stuff, most of the time when people try to solve this problem that I've seen lately, they do an alternating descent, because we have a chicken and egg problem, right? And just to step back for a second, this is what, to put in different language, what we have is a joint state and parameter estimation problem, right? That's all it really is from like a filtering world. And so one of the things that people do is do expectation maximization. Just choose a model, and then given the model, try to find the best initial condition. Then given that initial condition, try to improve the model, right? This like alternating idea. But here we tried to break that in half, because I'm afraid of alternating descent. I don't know how good that's going to work. So I said, okay, how can we make this a joint estimation? And this exact idea of having auto-differentiable data assimilation shortcuts us through that, or it prevents us from doing this EM and instead makes things joint. Yeah, Cheyenne, thank you. Yeah. So it turns out that I found out later that the particle filters were the first ones that people did this for, and they found them very expensive. So there's an interesting trade-off here where, so there is a particle version with ENKF, not a particle filter, but it's particle-based, right? That also seems to work well. But basically what you find is that the more complicated your data assimilator is, then the more complicated the gradient of the loss with respect to parameters through that process is going to be. So you're going to have a higher fidelity initial condition, potentially, conditioned on a model. It's a more accurate DA, but then getting the gradients of that initial condition with respect to that process becomes more complicated, right? And so I think there's an interesting trade-off there in what's the sweet spot. And perhaps there are senses in which you should start out with a cheap data assimilator because you just want gradients, and then later on you want to refine and maybe use something more sophisticated. So yeah, so just to give you guys a picture of what this actual method is, this is just one method, saying, okay, you give me data which are coming from the Lorenz 63 system. You only give me the first component, you give it to me noisily. So that's the yellow dots, okay? And I'm gonna, on the left side, this is my warm-up phase. So basically, I'm going to run DA. I'm actually picking the boringest DA I could come up with, which was 3D var with a constant forcing gain. And we can do cooler things, as Cheyenne said, but what if this is good enough, right? Start there and move from there. So we're going to run 3D var through the data using my sort of initially bad model. That's going to produce an initially kind of bad initial condition, and then I'm going to make a forecast, okay, using that bad initial condition. And now I want to update the parameters of my model using the gradient of the loss with respect to those parameters. And so the loss is just defined as the quality of the forecast in squared error on this forecast window here, which can be short, by the way. Fast forward, I'm showing you that I'm training on very short forecast windows, but I'm going to forecast really long in the test phase and be good at it. So don't worry, okay? So yeah, so this is where my error comes from here. And if I changed the model, right, this is the sensitivity of the loss with respect to parameters. If I change the model, two things change. One thing is that given this initial condition, I get a slightly different solution, so I can improve the fit. The other thing that happens is if I change the model, the entire DA process becomes different, right? Because now I have different weighted beliefs about, where the state is likely to be. And so what that effectively does is changes the initial condition. So it accounts for the two sources of variation for why my bad model is currently not working that allows me to zero in on the right one. And this worked surprisingly well. So I focused on this case of partly observed Lorenz 63. You only get the first component and nothing else. And I just want a good model for that first component. And what I found is lots of methods could give me pretty good trajectory style forecasting. But what was much harder is to find a method that had very good long-term stability of the invariant measure. What I mean by that is that maybe I ran reservoir computing and then I get some nice flips and oscillations here, but then if I run it for another 100 time units, this guy collapses to a periodic orbit or a fixed point. So that makes me sad. I said, well, I didn't really learn the correct right-hand side because the right-hand side, if I integrate it forever, it just stays looking like this. So that was the goal, is find a method that actually uncovers a right-hand side that is correct enough to maintain the invariant measure. And you might notice that I picked the right answer in the dimension of the hidden state here because I had Lorenz 63. I said, oh, well, there's two missing things, so I'm going to give myself two missing things to infer. But I also picked 10 just to try something else, and it worked just as well, actually. Okay, so as long as you have enough, you're good to go. Okay, how am I on time, by the way? How much time do I have? Oh, nice. Okay, so that's that. Let me move on. I'm going to skip this. So we can apply it to bigger systems, and then we had to learn the gain instead. So that was the one step up. Still constant gain, but I learned it. And for the Lorenz 96 multiscale system, what was cool is that the gain we learned actually you can see, if we sat here longer, this reflects the covariance structure that you would see when you write down the model. So this kind of heat map analyzing the gain is really connected, turns out, to the covariance structure of the model that it was learning, which is cool. So maybe this is some inspectable AI or whatever, right? Anyway, okay, now I wanted to switch gears and talk a little bit about reservoir computing. I want to complain a little bit. I want to ask some questions. And yeah, so that's where I'm going to go here. Okay, so I have like 6-7 minutes. That's where we're going to go. So I'm going to remind you, this is what a reservoir computer is in discrete time. Okay, so you have a sigma nonlinearity, and then you have a linear transform on the observed space. So what do we do with reservoir? Just to remind, we randomize and we fix the weights in the hidden state, fix the initial condition, and then if you give me the data of X and all of those fixed parameters, then I can actually just solve for RK for all time. That's given. I don't need to, I can just solve 5B basically. That's all given, no big deal. And then if you give me 5B, this is awesome because now I can do a linear regression and fit to XK. So I just infer C, which is a linear inverse problem. Okay, so here's a question for y'all. If it was actually a fully observed system, so say XK represents the full state vector of the original system, what is the best choice for W1 that I can make? Does anyone have any thoughts on this? This is where I get to have my water. For real. Yeah, Tom.
I would say there isn't really, that's a choice, but there are a lot of bad choices.
Really?
Just want to avoid symmetries. You don't want it signal synchronized with each other within the reservoir.
Okay.
So there isn't really the best choice, but you can certainly make a bad choice.
Okay.
Or just avoiding bad choice. It doesn't have to be random. Just avoid the symmetries.
I see. Anyone else want to comment on that?
I think based on the golden ratio, you get a nice irrational.
It needs to be the shape of my credit card?
No, not that, but the golden ratio being very irrational. Great synchronization.
Okay. Other thoughts? These are really interesting. One more? No? All right, don't hate me, but I think this is an easy and simple answer. I think that the answer is that it should be 0. Okay, the right answer, I believe, is 0. W1 should be 0 because there is no latent dynamics, there's no memory, there's no missing state. So this RK is only really giving me expressivity. Okay, how can I get expressivity of R really easily? I kill W1 completely. I set it to 0. Then what is RK plus 1? It's sigma of W2 XK plus B. Yeah, Cheyenne. Yeah.
So I have a question.
Mm-hmm.
Do you think this would be you're looking at meteor regime versus the neural canyon? Right? Because if you're in the neural canyon, there's volume out, right? So you get the random features. Now, if you feel that you are in the meteor regime, you have to move right? Then would you give me a different answer?
I don't know. I mean, I'm mostly thinking about deterministic systems here, but I'm pretty sure that the answer would be I'd rather just have an SDE.
Okay.
I think that would be my answer, that I'd much prefer an SDE than a weirdly wandering hidden state that I'm not sure what it means. Yeah. So just to kind of fast forward through what Cheyenne is seeing, right? So RK becomes a random feature, basically. That, like, exactly, that's what it is. And so if I were to sum them up using C, then xk plus 1 is J is just like the rows, right? So I just sum them up. Cj's are the coefficients, and then these are the random features. And if I take enough of them, in other words, a big enough reservoir, then I'm in a random feature limit. And in particular, for those of you who aren't familiar with this stuff, if you happen to choose sigma as cosine and you make the right choices about weights, this literally converges to a Gaussian process regression with a random basis, or what is it? RBF, whatever RBF stands for at the time, it's blanking. Radial basis function. Yeah, it converges to a Gaussian process with RBF kernel. Okay, so all I'm getting at here is that, you know, if we test a reservoir system on a fully observed state, we're not checking much about the reservoir itself. So here's kind of my gripe is oftentimes we apply reservoirs to partially observed systems, but those systems may have substantial Markovian properties on our observables. So my question to you is, do you ever worry that your reservoir computer is not really learning memory? And here's an easy sanity check, okay? The easy sanity check is you set W1 equal to 0 and retune the parameters and just ask the simple question of how well does that model perform? And if it performs, however much worse it performs than your original reservoir, that's how much memory you've learned. If they perform the same, then you didn't get anything out of the reservoir. And I'm only telling you this because I really struggled to get memory out of these reservoir stuffs. And that's what kind of pushed me to build these other methods and forced me to try and do backprop and all the things we're trying to avoid with reservoirs. But I love this reservoir idea. So anyway, okay. Here's another short sort of like gripe about RNNs and LSTMs that I'll give you. Okay, so on the left-hand side, here's a RNN or a reservoir computer, if you will. And what do we notice about it? Okay, what is the number of latent variables? It's the dimension of R, right? Cool. Where does the expressivity of this system come from? It comes with the dimension of R, right? The only way I can actually get an approximation of a dynamical system for this guy is if I send the dimensionality to infinity, right? Even if I'm trying to learn a finite dimensional system, the approximation limit of this guy is in an infinite dimensional regime, which feels unsatisfactory to me. I feel afraid of this a little bit, or I might wonder, right? On the other hand, what if I make subtle changes, which is I put a B in front of that sigma, so that now R is this right-hand side on the bottom is now basically a neural net, right? So I went up in dimensions using W1, but then I come back down to something. So now this guy's an approximator, and same thing up here. This is these are function approximators. So what does this give? Whoops, whoa. So what does this give me? So still, the number of latent variables is the dimension of R. That's good. I mean, that feels right. But now I get expressivity that really just depends on the parameters and like their widths and stuff like that. And what this does is it decouples the dimension of the dynamical system from like the particular expressivity or the types of functions on the right-hand side it needs to represent. So that means that for example, I can use infinitely many parameters to get really good approximation, but still in a finite dimensional space of dynamics. So it's just thinking about when do we like force ourselves into which of these regimes, and just kind of being mindful of that. Okay, final kind of question. Here I could just rewrote the reservoir in continuous time. I like continuous time. How do we get these to work well in continuous time? And in particular, what distributions do we need to choose for W1 and W2? The stability conditions change for continuous time, but we know things about them. We can linearize, but frankly, I tried a little bit and I don't really know the right answer. So this is sort of a question to all of you that like, I would love to have a method that does this, where you randomize the hidden states and then I get a ODE that really works for reservoirs, but I just haven't really gotten it to work. Okay, so here's some conclusions. We can learn ODEs from partially observed noisy data by embedding state estimation techniques within the optimization. So you could even use this to tune DA parameters. If you have a big model or one that you're afraid of all this like backprop stuff that I'm telling you about, which you should be, all of this still makes sense. We just said we're doing an optimization, so you could still do this in a derivative-free sense, right? So if you have a particle-based optimizer, you could try the same stuff. And it actually could afford you a lot more flexibility. And also using this for trying to model some endocrine dynamics with patients with diabetes. Reservoir computers and random feature methods are connected with WR equals 0. We're actually just approximating a Markovian model, like a Markovian GP. When it's not 0, something else is going on. We're actually organizing a small ICIAM symposium with Ali Dunbar and Nick Nelson to talk more about this. So there's another random feature, maybe on a Banach space, that's going on when WR is non-zero. So we want to get people to answer this for us. And yeah, I'm going to need a job soon. So yeah, and I really would like to apply a lot of this stuff in like biomedical contexts, and also still work on these foundational things and kind of combine that work. So cool. I want to highlight lots of related work. So many people here at this conference have been very influential for, we're standing on the shoulders of giants. So yeah, so thanks to many of those people. Thanks to all of you who've made this such a cool week, and Boumediene and the organizers in the fields, and thanks to Caltech, Andrew, grad students, Mathieu reviewed my slides, told me to cut a few. You're welcome, because this was already long, so you can thank him for why you're leaving now. And yeah, that's it. I'll stop.